Science Gateways Community Institute has been funded by the National Science Foundation to provide support to the community of gateway developers and users. And we do that in three main ways. The first area is through support for building and running gateways. That includes consultants who can help you develop your gateway. It also who can provide advice about topics like user experience, cybersecurity, and sustainability. And we also have a catalog of gateways and software. And the second area in which we provide support is through education and training, such as this webinar series. And we do have all of our events archived on our website. We also offer a couple of programs that currently are available virtually, so they're easy to attend. One is the Gateway Focus Week, and the other is the Jumpstart Your Sustainability Plan. Those are both opportunities to think about making your gateway last into the future and reach its desired audience. We have a number of student-focused programs, including a recently completed hackathon. There will be one, I think, at supercomputing as well, and then a coding institute that just also ended. And we have lots of resources on our website. And then finally, we're about the community that comes together around gateways. This includes our annual conference. There will be a virtual one in this fall, and then finally an in-person one in the coming spring. The community forum is a Google group that all are welcome to join. And we have some other programs involving ambassadors and collaborators. So with that, we just one last request from you. It's helpful if you do give us feedback about how this webinar was for you as far as usefulness. I'll be posting this link in the chat also partway through the event presentation to make it easier for you to provide us with your feedback. So with that, I will hand this off to our presenter today. I'm really delighted to introduce you to Smruti Padhy, who is at the Texas Advanced Computing Center, and she's going to be talking about TAPIS and the API and all sorts of technology that I don't know about, but you will soon know more about. So with that, go ahead, Smruti.
Thanks, Catherine. Let me share the screen. Okay, so are we able to see my screen?
Yep, looks great.
Okay. Okay, so hi everyone. As Catherine said, I'm Smruti Padhy. I work at the Cloud and Interactive Computing Group at Texas Advanced Computing Center at the University of Texas in Austin. So today I'm going to present our work as how TAPIS Streams API can help you with real-time streaming data event-driven workflow. This work is done jointly with TAPIS and Abaco team at TAG and at the University of Hawaii, and with collaborator from Marshall University, West Virginia. So first, we would like to thank National Science Foundation for funding this work. TAPIS and Abaco team to putting this all together and building this service, and our early adopters who provided the valuable feedbacks in building the service. So here is the talk outline. So I will first briefly go over the challenges one faces in a computational research, TAPIS project overview, motivation behind our work, Streams API overview, the high-level architecture, design, an example science use case, and some of the experiments that we did to validate the design and the service. And in the end, I will provide steps that will allow one to build event-driven workflow with Streams API, and conclude the talk with some upcoming features. Okay, so with advancement of science and technology, a researcher faces many challenges. in computational research area. So computational research often involves a multi-stage endeavor, which involves like interacting with instruments, that is getting raw data from various instruments, sensors, which might be geographically distributed. The other challenges are the rate at which the data are generated and the different data types. The second stage is like performing data processing on those data, which might involve like quality assurance, the ETL scripts and some machine learning on different platforms. The third is the model simulation, which would involve like having the simulation run on HPC platforms. And in the end, the last challenge would be to managing, sharing, and publishing these results and data once these experiments are completed for repeatability and provenance purpose. So designing such cyber infrastructure to support such an endeavor also depends on science-based use case workflows to address the need to for the cyber infrastructure to perform distributed computational research. TAC, in collaboration with University of Hawaii, have proposed and built TAPIS framework. Now let's see what is TAPIS project. So it is an NSF-funded web-based computing framework to support distributed computational research, which enables a researcher to leverage computing resources across various institutions. So more technically, it is a set of hosted multi-data center REST APIs together with set of languages, SDKs, CLIs for securely managing data, exchanging code on HPC, HDC, and cloud systems. Some of the higher level TAPIS objectives are to provide researchers with the ability to manage and execute workflows, track their analysis for provenance purpose, reproduce their analysis, and share their data workflow application computational research with collaborators. And this TAPIS enables so that the researcher doesn't have to install or support any complicated stack of technology. So these are some of the primary capabilities of TAPIS framework. So it has this hosted APIs and services like system files, apps, jobs that enables interaction with data and execution of code on HPC, HDC systems. The metadata service, which manages large collections of document objects, Abaco functions. So this allows execution of containerized function in response to messages, authentication module. Then we have containerized apps, which are the first class support for containers. Streams, that service, it allows the stores and process sensor data in real time, and security kernel, which is a decentralized secret store and authorization subsystem. So this all yellow color thing like the containerized apps, streams, and security kernel are new in the TAPIS v3. And in this talk, we will be focusing on the stream service. So motivation. So what is the motivation for designing streams API within TAPIS framework and support for event-driven workflow for streaming data? There has been a rise of IoT devices, instruments, and sensors to observe and measure almost everything. So this has led to increase in time series data, which in turn has led to increase in demand for support for storing, processing, and analyzing time series data. Also, there are many science use cases based on monitoring now require ongoing data processing as the data arrives and notification of any anomaly detected in those data. However, there are many computational, existing computational infrastructure and systems are built around batch computation. So there are also few ready off-the-shelf solutions to handling streaming data. and some such as the Elasticsearch, Prometheus, Apache Kafka, Amazon time series. There are also geoscience time series data storage stores like Hydro Server, Voice, and CHORDS. Now, many of these solutions aims at industry use cases, and they lack either integrated collaborative and special support, or they are too expensive or complex to manage by researchers. So this leaves a gap for hosted academic streaming data solution capable for supporting data event-driven computational workflows. Now, to help to address this cyber infrastructure need and fill the gap to support streaming data for science, University of Hawaii and TAC have developed an open source unified middleware API and infrastructure platform with collaborative features. And this middleware is known as TAPAS v3 Streams API. And as the name suggests, the TAPAS Streams API is one of the hosted service and API in the TAPAS project. So TAPAS v3 Streams API at high level, it is a hosted real-time streaming data storage, processing, and event service. It is an API for storing, analyzing real-time streaming data from geographically distributed sensors. It is built on top of CHORDS and extends the CHORDS data model, that is sites, instruments, and variables. It adds one more abstraction to it called projects, and also allow annotation with additional metadata. Now, with this additional abstraction and metadata, such as the geocoordinates of the sensor, this also allows for searching and slicing of data using both geospatial and temporal indexes. So in our previous work on Streams API, we have focused primarily supporting the first stage of streaming data lifecycle, that is the data ingestion of the time series data, data storage for fast processing and for long-term storage, data annotation for data curation and discovery, data archival and data replication, and data retrieval with temporal and spatial support. In this work, our aim is to build support for second stage of handling streaming data, that is adding analysis capability by supporting real-time streaming data event-driven workflow. Now, designing such capability will require defining evaluation functions on multiple incoming data streams, evaluation of multiple measurement variables to trigger analysis workflows, integration with TAPAS Abaco, which is a function as a service platform, and then integration with computational applications and job service to do more in-depth analysis with batch job service executed as TAPAS apps. Also, the aim is to add a collaboration support, that is a role-based access, allowing multiple users to share and manage both data and workflows. So in this work, our focus is to integration with the TAPAS Abaco to enable event-driven workflow for streaming data. So before diving into the design of Streams API, let's quickly review the high-level architecture and some of the background. So this is TAPAS v3 high-level architecture of Streams API integrated with other components of TAPAS v3 and CHORDS. So the Streams API uses security kernel service to check if the users or the devices are authorized and authenticated for the requested action. It uses the meta service or the metadata service as the backend database to store information about the different stream service resources, such as projects, sites, instruments, and variables. it integrates the CHORDS with this platform to leverage a streaming data model. The CHORDS uses the time series database InfluxDB to store the measurements value obtained from the variables. TAPIS V3 can also read and write directly to and from InfluxDB. Now, the Streams API also integrates with the Kapacitor, which is the native data processing engine for InfluxDB for processing and enabling alerts and event service. The Streams integrates with Abaco and Jobs service to enable the processing of analysis workflow on alerts. Okay, so there are some background involved in this architecture. Now, to support the storage of resource metadata, the Stream API leverages the TAPIS metadata API. Now, the Streams metadata objects are hierarchical with the projects at the top. Sites belongs to a project, and instruments belongs to a site, and variables belongs to an instrument. So this basically extends the CHORDS metadata object hierarchy, and having these projects which is at the top, and the sites, instrument, variables are under the project. So CHORDS, the Streams API integrates with the CHORDS. So CHORDS is a cloud-hosted real-time data service infrastructure that provides a graphical interface for acquiring, storing, and analyzing data streams via cloud service and the internet. So it leverages this InfluxDB and MySQL database, and the basic data models, as I already mentioned, have sites, instrument, variables, and measurements. And all the metadata for CHORDS are stored in MySQL, and these measurements are written into InfluxDB. So measurement data. So in Streams API, the measurement data are stored in InfluxDB, and we are currently supporting float data types, and these are written in the context of instrument variables and with timestamp of ISO 8601 format. Capacitor. So the Streams API integrates with the Kapacitor to enable the event-driven workflow. And it is, as mentioned, it is a native real-time data processing engine for InfluxDB 1 series. And it has the ability to process both batch and real-time streaming data from InfluxDB, and it can define monitoring and processing tasks to perform on those incoming data. Then the last piece is the Abaco function as a service. So it is Abaco platform allows one to define computational primitives called actors of functions using a Docker image. It allows messages to actors using HTTP. Abaco queues this execution for each message, and then Abaco asynchronously launches a container for each message, and then execute this containerized function in response to these messages. These actors can store results, logs, and Abaco can measure the resource uses. Now let's dive into some more details of Streams API design. So these are the Streams API resources. So in our previous work, we have focused on resources related to data ingestion, storage, and query. That is the project, which is a logical grouping of sites, site, which is like a geographical location on which one can have one or more instruments, instrument, which is a source of related measurements, variable, which is like a particular measurement made by an instrument, measurement, which is a single observation of a sensor of an instrument. So in this work, we have added two new resource called channels and templates to enable this workflow. So channel is an abstraction for pre-processing of measurements to raise an alert and initiate the execution of workflow analysis. And template is a reusable script in channel definition that defines a monitoring task. So this is an example of streaming data event-driven workflow supported by Streams API. So this figure illustrates that data streaming from two instruments A and B and being evaluated by 3 Boolean conditions as shown in the figure. Now each channel defines a set of conditions to evaluate the data as it is being ingested that results in 2 alerts. So for example, channel 1, the condition being evaluated is if the value of var1 in instrument 1 is less than 5, then trigger action 1. Now, if you see the data being ingested for instrument A and var1, it is 2. So this condition evaluates to true. So it triggers an action 1. Now, this action could be anything like call to a third-party API calls or execution of Abaco actors or status jobs. Now let's look into how Streams template API is designed. So before going into the template, let's first define a task. So a task is a work to be performed on a streaming data set. And template, alternatively, we also call it as template task, is a reusable definition that represents a task. Now, it has the task has 4 sections. So the first one is the monitoring of incoming measurements data. Second is aggregating the values. Third is raising alerts when the measurement value satisfies specified Boolean conditions. And the fourth is sending the critical data that triggers the alert to perform specified actions. So templates need to be created before defining a channel, and in Streams API, we will be providing some predefined templates for users. And template actually enables reuse of the template script with different conditions and alerts actions, so multiple channels can be defined. So here is an example of a template script. So this template is a tick script defining a task with variables that are set during channel definition. So as I have mentioned, so it has 4 sections. The first section is declaring the tick script variables, and these variables are nothing but some of the lambda expressions which are of the form, which is nothing but the Boolean conditions like the cret1, the var equal to 8 and the instrument ID is 11, just indicate that we are looking into the value for the variable ID 8 and the instrument ID 11. Then the second section is to setting up tick script variables to filter data streams. So these variable cret1, 2 get substituted in this expressions, and that allows it to filter the data streams. The third section is the aggregation of values. So combining these 2 data streams coming for 2 sensors, that aggregating, and that allows it to get evaluated the final functions and allows the alert definitions. So note that this is a Kapacitor tick scripts, and Streams API leverages it. It wraps this Kapacitor's template API and task API to provide the template functionality within Streams API. Now let's look into the channels design. So channels, so it is an abstraction for pre-processing of real-time streaming data to trigger alerts based on a function of the variables and initiate analysis on the data. A function of the variable, the Boolean criteria and condition on the variable's values. So when the evaluation is true, an alert is issued and additional processes can be initiated, such as Abaco actors or Tapas jobs. The template task needs to be created prior to the channel creation, and a channel actually defines a task for the capacitor using this template task, measurement variables with the actual Boolean conditions, and with a set of action when the alerts are raised, this set of actions need to be performed. So here is an example of channel definition. So it requires a channel ID, template ID of a pre-created template, instruments IDs, condition, which is not conditions, that is which involves this instrument and the sensors with the conditions that we are trying to evaluate, and then the actor ID here in this case, which is like when an alert is raised, this particular actor is executed in the Abaco platform that does some analysis on the data. So here is an integrated architecture of Streams API supporting event-driven workflows. So as the data arrives in the Streams API, it is written directly into InfluxDB. Then the data gets copied into the capacitor through subscriptions. Capacitor evaluates the functions provided in the channel definition. If it exceeds certain threshold, it raises alerts and sends this data to Streams API. The Streams API pre-processes this alerts data and initiate the execution of an actor in the Tapas Abaco platform. So once Tapas Abaco successfully queues this execution, sends an execution ID back to Streams, and which user can use to keep track of execution. And all the data are then stored in the metadata service. So now let's look at an example science use case. Okay, so we have been collaborating with the researcher from Marshall University, and they have been monitoring water quality of streams in Appalachia. They have been leveraging 3 NSF-funded projects, the AFI, SCIENCE, and GeoF. And the workflow involves collection and sharing of water quality data using EPS, WQP, and WQS API. CHORDS instance for continuously monitor sensor data, with the need for the on-the-fly processing potentially on the remote HPC. Now they envision to get benefited from the real-time analysis, and the goal for integrating this water quality science gateway with the Tapas Streams API is to detect anomalies in the measured data, correct for any calibration errors, generate alerts when certain thresholds are exceeded, computing some kind of rolling statistics, or combine with other data sources, use some kind of machine learning and image processing, and push some summary of data to the water quality database. Now, with the given this use cases, we did some experiments to validate our architecture and the design and the service. So we obtained this real-time data set from 2 sites from Ohio River, and each site hosts 2 instruments. Each instrument has multi-sensor probes monitoring different properties for water quality study. And these data are obtained by the researcher at Marshall University every 15 minutes for 30 days. Now, these sensors are actually monitoring all these variables that you see in this table. It's like 15 variables. For our experiment purpose, we monitored only 4 of them. like temperature, pH, turbidity, and the dissolved oxygen. Now you see this range of values that we obtained for each of these instruments from this data. So in our experiment, we generated this, or we used this data and generate this measurement at the interval of 0.1 second, 5.5 second, and 1 second instead of 15 minutes, so that we can stress the system. Now, to do our experiment, we first created 3 channels for each instrument, and each channel actually used used 1, 2, and 3 variable templates for channel creation respectively. One variable condition looks like the temperature is greater than 9 degrees centigrade. 2 variable condition is like temperature greater than 9 degrees Celsius and pH value less than 5. 3 variable condition we used is temperature greater than 9 and pH less than 5 or turbidity greater than 500. We deliberately injected data that could satisfy the Boolean conditions, the above Boolean condition, and raise alerts. And what we have found is that the number of alerts generated for different rate of measurements for different number of conditions are always same as the number of alerts expected. And this gives us confirms the designs, what we are trying to achieve of supporting the event-driven workflow. So especially we have shown this for this water quality data monitoring use case. Now, how the Tapas Streams API can help you. So these are some of the steps for building event-driven workflow with Streams API. Like if you are a Science Gateway developer and want to use the Streams API to build an event-driven workflow, then one can go through these steps. The first one is that we need the real-time sensor data as float type. Create an Abaco actor with the Abaco platform, which will have where all the analysis scripts are containerized. Then create the stream resources, the project size, instruments, variables. Create templates with the monitoring tags. Create channels using the template and the Abaco actors. And finally, to execute the event-driven workflow, one needs to post measurements to channels using the measurement Streams measurement API. Now, as you see, it has like several steps to it, and it uses the Abaco APIs to create Abaco actor. It uses Streams API to create all these resources. It uses templates API with to create a template, and channels API to create the channel, and measurements API to post it to the measurements. Now, it may look that one needs so many APIs, but we have also built Python SDK, a Tapas Python SDK, which is TapiPy, which has all these APIs, and one can easily use it. We also have Jupyter Notebook, which is a Docker image with all the necessary packages installed, like the TapiPy. And if one wants to build a event-driven workflow, then one can take this notebook, start this Docker container, and use the Jupyter Notebook with the examples. So there is less time to start working on this thing. Now with upcoming, so we have some upcoming features like advanced search API for geospatial queries, ontology support for metadata. A work in progress is right now with integrating Tapas job service with streams, and additional data type support and UI for managing streams, data, and events. And we also welcome any feedback from our early adopters and community. Thanks. So here are some of our project informations, and you can join us with a Slack team. Thanks. So any questions I can take now?
Yes, so we'll open up for questions now. There's a question that just came in from Rick. He asks, have you determined practical maximum sampling rates with and without condition checking and message sizes? Then he has a part 2 to that question, which is also, do you have a scheme for securing data at rest, assuming SSL for data in motion?
Okay, so for the first question, we have some performance testing we did. I don't remember the exact numbers, but we did have some results in one of our paper on the package size and the sampling rate.
Okay, is that, Rick, if you want to speak up too, if there's any follow-up you have for that, you're welcome to.
Yeah, I can share the paper. I don't exactly remember the rate.
Yeah, that'd be great. Yeah, I was just wondering if you had done any like experiments on, you know, how fast you can pump information through this system. But it turns out, depending on the size of your whatever array you have at the end, you may end up with fairly large instruments, especially if you're using some imaging device to sample with. So that's the counterpoint. I mean, especially if things are way out on the edge, you may have issues with needing retransmission, or, you know, message size causing message loss, things like that.
Yes, yeah. So Anaga has said we tried sampling rate of less than 1 second to stress test our system. So the sampling rate we did is 1 second. Yeah, and regarding the imaging data, yeah, currently we are just supporting the float data type, and I agree with the challenges with the imaging data with that.
Thank you.
Great. There was also a question and a request from Amit. He first of all asked if you could share a link to CHORDS, and we could certainly add that to our archive when we post this on our website. But he also asked the question: does the Streams API use synchronous or asynchronous processing on the server side?
So all the Streams API right now are synchronous, but when it triggers an action, which when the execution happens at the Abaco platform, or it triggers and taps jobs, so that is asynchronous. Great.
And thanks, Anaga, for posting the link. We'll grab that and also include it on our website. So far, there are no other questions, but I'll invite anyone to either speak up or post them here in chat. We'll give you a minute or so to think about other questions. And while we're waiting, I'm gonna share with you just some information about our upcoming webinars. Just a moment here. So we are not having any webinars in August, but we will have 2 coming up in September. One will be on September 8th at the same time about the Science Gateway Cybersecurity Mini Guide, which is being developed by Mark Krenz along with some other folks here at Science Gateway's Community Institute. And then on September 29th, it'll be a bonus session. This is not the actual title, but essentially an opportunity to get the latest on how you can make the most of our services and what opportunities and changes are going to be happening as we head into year 6 of SGCI. So, so with that, I'm looking to see if there's any other questions coming along. So far, it seems like folks have their questions answered and must be pretty satisfied. I'm curious what has been the most challenging aspect of this for you or for your team. I know you have a bunch of people working on this, and I know you have more than one source of data contributing to your testing and so forth. What makes this has made this particularly challenging in an interesting way?
Yeah, so I think the most challenging is to actually building it on top of the several services in our TAPAS framework. So it leverages several services, and then it integrates with the CHORDS, and it integrates with the Kapacitor. So, and also it involves lots of people who have expertise in working in their services, and then we are the person who actually mediate with the integration of all those components.
Yeah, that makes sense.
Yeah.
I'm sorry, were you going to say anything else?
No, so I just wanted to thanks our collaborators like Jack Smith from Marshall University for providing us with all this data for testing our services.
Yeah. So far, no more questions have come up. So I guess you're gonna win an award for being really clear. It's really great. Thank you. So I want to thank everyone for joining us today for this webinar, and hope to see you at future webinars, and do let folks know if you have colleagues who would enjoy hearing about this as well. I know that Smruti is also going to be talking about this at PERC next week. So, and
yeah, also another announcement. So we will be giving a live demo of TAPAS API at the TAPAS user meeting at PERC. So if possible, please attend that. You will get much more information about TAPAS framework. Oh, that's terrific. Is there, maybe you could let us know what time that event is, so we can add that to our web archive information, so that those who are registered for PERC could find it easily. That would be great. Yeah, sure. Yeah, we will share. Sean put that in. Sean, thank you. Yes, yeah. So Sean already put it there. Yes. Awesome. Like instant gratification. Awesome. Well, thank you, everyone. I will we'll look forward to seeing you again, either PERC or at future webinars. So take care and enjoy the rest of your day. Yeah. Thank you so much. Thank you.